In any torpedo engagement, there is one variable that determines everything. Not the depth of the ocean, not the speed of the submarine, not the weight of the warhead. Time. A target gets exactly as long as the torpedo needs to reach it. That is the complete geometry of the problem. The moment a torpedo is launched, a clock starts. When the clock runs out, the engagement ends. The fastest conventional torpedoes in the world, the American Mark 48A DCAP, Soviet designs from the same era, operate at roughly 50 to 55 knots. At an engagement range of 11 kilometers, that clock runs for approximately 13 minutes. 13 minutes from the moment a sonar operator detects a launch signature. 13 minutes to confirm the contact, report it, sound general quarters, issue orders, deploy countermeasures, change course, accelerate. 13 minutes is not comfortable. Under combat stress, it is not comfortable at all, but it is workable. It is enough time for the problem to be survivable. In the late 1960s, Soviet naval engineers looked at those 13 minutes and decided they were a gift they could not afford to give. What they built gave a target 108 seconds. To understand how 108 seconds is even physically possible, you have to start with the thing that makes water the most hostile environment ever built for speed. Water is 800 times denser than air. Every torpedo, every submarine, every ship ever built is continuously fighting that density. The resistance doesn't grow at a steady rate as speed increases. It grows with the square of velocity, meaning every small increase in speed demands a disproportionately large increase in power. Double a torpedo's speed, and you need 8 times the engine power to maintain it. 8 times. That's not an engineering shortcoming, that's physics. You can build a better propeller, a more efficient fuel, a lighter hull. None of it fundamentally changes that relationship. The result is a practical ceiling. Fastest conventional torpedoes operate at 55, maybe 58 knots in ideal conditions. Getting meaningfully beyond that doesn't require incremental improvement. It requires something that doesn't exist, an energy source dense enough to overcome the math. There is also cavitation. Any surface moving fast enough through water creates low-pressure zones. Along propeller blades, along hull surfaces, wherever water has to accelerate sharply to get out of the way. When that local pressure drops below the vapor pressure of water, the water doesn't stay liquid. It boils. Not from heat, but from the pressure drop. It turns into vapor bubbles. Those bubbles collapse violently when they move back into normal pressure water. Each collapse sends a shock wave into nearby metal surfaces. Over time, cavitation erosion destroys propellers. But the immediate tactical problem is noise. Cavitating propellers produce a distinctive acoustic signature that passive sonar can detect at significant range. A submarine's ability to remain undetected depends partly on staying below the cavitation threshold. Propeller design, hull coatings, pump jet propulsors, enormous engineering resources dedicated to pushing that threshold higher, to delaying the speed at which the noise begins. The engineers at NII-24, the Soviet Navy's Research Institute for Underwater Hydrodynamics and Acoustics, spent years working on exactly this problem, studying cavitation, trying to suppress it, trying to understand it precisely enough to prevent it. At some point in that research, someone asked a different question. Not, how do we eliminate cavitation, but what happens if we take it all the way to its logical extreme? The concept behind the answer is simpler than it sounds. In ordinary cavitation, bubbles form locally and collapse chaotically. The weapon's surface is still mostly in contact with water. The drag reduction from those bubbles is minimal, and the noise and erosion make it a net negative. But there is a state beyond that, a state where the cavity doesn't form locally, where it forms at the nose of the weapon and extends backward, growing as speed increases until it completely envelops the entire body. The weapon is no longer in water. It's inside a continuous envelope of water vapor and gas, separated from the ocean by a stable boundary. This is supercavitation, and inside that envelope, drag doesn't decrease, it collapses. The reduction factor is roughly 900 times less drag, not 10%, not half, a factor of 900. At that point, the relationship between power and speed that makes 55 knots the ceiling for conventional torpedoes no longer applies in the same way. The weapon is effectively moving through gas, not through water. The physics of what's possible change entirely. Question for the engineers at NII 24 was whether a stable supercavitating envelope could be created around an actual weapon, something 8 meters long, armed, and required to function reliably at depth in an actual ocean rather than a controlled laboratory tank. The answer took approximately a decade to build. The first component is the nose. On a conventional torpedo, the nose is carefully streamlined, a shape designed to let water get out of the way with as little disruption as possible. The design goal is smooth flow. The Shkval's nose is a flat disc, blunt, not streamlined. This is not an engineering oversight. The disc, the cavitator, is designed to interact with water as disruptively as possible. When it hits water at speed, the pressure differential at its rim is so abrupt that the flow cannot follow the surface of the weapon behind it. Water detaches from the nose and forms a growing cavity. Below about 50 knots, that cavity is partial and unstable. Below, the weapon is still mostly in water. As speed increases, the cavity extends further backward along the hull. At around 180 knots, it reaches the tail. Above that threshold, at full supercavitation, nothing touches water except the rim of the nose disc. The weapon is, at that point, encased, flying through a gas shell of its own creation inside the ocean. To steer inside the bubble, conventional fins don't work. Fins generate lift by interacting with surrounding fluid, and inside the cavity, there is no fluid. The Shkval steers by tilting the cavitator disc slightly. Changing the disc's angle shifts the cavity geometry asymmetrically. The bubble pushes more on one side than the other. The weapon responds. The control authority is limited. The Shkval cannot maneuver sharply, but it is enough to maintain a course. The second component is gas injection. A natural cavity at shallow depth can sustain itself on the vapor pressure of water alone. But at operational engagement depths, where ambient water pressure is significantly higher, that natural cavity would collapse almost immediately. The surrounding ocean closes in and kills the bubble. The Shkval solves this by injecting gas into the cavity continuously. The rocket motor routes a portion of its exhaust gases forward through internal ducts. Hot combustion gas flows into the base of the cavity, maintaining its pressure against the surrounding ocean. This injection system is what makes the Shkval viable at combat depth rather than only in shallow coastal waters. The third component is the motor. A propeller inside a gas bubble generates no thrust. It has nothing to push against. The Shkval uses a solid fuel rocket motor. A rocket doesn't interact with its surrounding medium. It generates thrust by directly expelling combustion products backward. It functions identically in water, in gas, in vacuum. The environment inside the cavity is irrelevant to how the motor works. The environment in the fuel burns for a fixed duration. That duration limits the Shkval's range to approximately 11 kilometers. At 200 knots, 11 kilometers takes 108 seconds. Let me make that number concrete. An F-16 fighter jet comes in for landing at approximately 155 knots. At 200 knots, the Shkval is moving faster than a fighter aircraft on final approach, not through air, but through water. A submarine-launched torpedo is not supposed to move faster than a landing jet. Nothing in water is supposed to move that fast. The fastest fish in the ocean, the sailfish, tops out at around 68 knots and only in short bursts. The Shkval sustains 200 knots for the full length of its 11-kilometer run. The fastest conventional torpedo covers 11 kilometers in about 13 minutes. The Shkval covers the same distance in 1 minute and 48 seconds. The difference between those two numbers is not a speed improvement. It is a different category of problem for the crew of the target vessel. In December 1977, the VA-111 Shkval completed its acceptance trials in the Norwegian Sea. The recorded speed, just over 200 knots. The weapon entered Soviet Navy service. At that speed, 108 seconds is what the crew of a target vessel has from the moment a launch is detected. Consider what that actually means aboard a warship. On a NATO destroyer, getting all crew members to battle stations from a general alarm takes, under good conditions, with trained crew in regular exercises, around 4 to 5 minutes. The alarm sounds at the moment of launch detection. By the time the Shkval arrives, most of the crew is still moving through corridors. No one has reached their station. No countermeasures have been deployed. The ship has not completed a meaningful course change. 13 minutes is a manageable problem. 108 seconds is not a problem. It is a result. And then the complication. The same physics that make supercavitation possible create a constraint that cannot be solved with better engineering. It can only be worked around. Inside the gas envelope, there is no water against the hull. Standard torpedo guidance works acoustically. Active sonar, the weapon transmits pulses, detects the return from the target, adjusts course. Passive sonar, the weapon homes on the target's own acoustic signature. Both require acoustic energy propagating through the medium surrounding the weapon. Inside the Shkval's cavity, acoustic energy cannot propagate. The cavity is, acoustically, a vacuum. The weapon cannot hear, it cannot ping. It has no sonar contact with anything outside its bubble. Wire guidance is also eliminated. Most modern heavyweight torpedoes, including the Mark 48, spool out a thin guidance wire as they run, allowing the launching submarine to update course in real time. At 200 knots inside a gas envelope, that wire would be severed within the first second. The Shkval is, from the moment of launch, completely isolated. It receives no information. It makes no corrections. It travels in a straight line on the trajectory computed before the trigger was pulled. The targeting solution must be perfect before launch. The operator must predict the target's position 108 seconds in the future, accounting for its current course and speed, before firing. If the target alters course after launch, the Shkval arrives where the target was, not where it is. Against a ship that holds course and doesn't react in time, a solvable problem. Against a ship that detects the launch acoustically and maneuvers immediately. And modern warships have increasingly capable acoustic monitoring systems. The straight-line trajectory is a serious liability. The engineers had created the fastest underwater weapon in history. It could not guide itself to its target. The Soviet Navy's response to this constraint was not an engineering solution. It was a yield solution. The initial operational variant of the Shkval carried a nuclear warhead, approximately 150 kilotons, roughly 10 times the destructive power of the Hiroshima device. At 150 kilotons detonated underwater at combat depth, the destructive radius is measured in kilometers. A ship doesn't need to be at the precise impact point. It needs to be within the lethal zone. And the lethal zone is large enough that no course change in 108 seconds can take the ship outside it. The guidance problem, which was insoluble at conventional explosive yields, disappears entirely. The Shkval doesn't need to hit the target. It needs to arrive in the target's general vicinity. Close enough is close enough, because at 150 kilotons, close enough means destruction. A weapon that couldn't be guided became, by that decision, a weapon that didn't need to be. There is a specific irony in this resolution. The Shkval program represented years of precision engineering, exact control of cavity geometry, carefully calibrated gas injection, optimized disc angles. All of it in service of a weapon whose accuracy problem was solved not by better guidance, but by making precision irrelevant. When the Shkval entered Soviet Navy service in 1977, Western intelligence gradually assembled the picture of what it was and what it could do. The tactical geometry it created was straightforward. A surface ship operating within 11 kilometers of a Soviet submarine carrying Shkvals was inside the weapon's engagement envelope. With the nuclear-armed variant, being inside that envelope and being destroyed were functionally the same outcome. Anti-submarine warfare doctrine for carrier strike groups had to account for this. Standoff distances for escort ships increased. The protective ring of frigates and destroyers around the carrier had to extend further out, far enough to keep submarines beyond Shkval range. A larger perimeter requires more ships to maintain adequately. More ships mean more logistics, more fuel, more coordination overhead across a larger area of ocean. There was no technological counter to the weapon's speed. Nothing in 1977 Western naval arsenals could intercept a weapon at 200 knots. The acoustic signature of a Shkval at launch, the distinctive cavitation noise of a weapon accelerating through the supercavitation transition, was detectable. Detectable, but not actionable, in 108 seconds. The response was doctrinal. Accept that the weapon cannot be directly countered and redesign the geometry to reduce the probability of a submarine getting close enough to use it. A weapon that cannot be countered directly changes the shape of the water around it. Russia continues to operate the Shkval and its successors around it. An export variant, the Shkval-E, was offered for international sale in the 1990s with a conventional warhead and reduced performance specifications. This generated a sustained arms control dispute. The United States argued that selling supercavitating torpedo technology to Iran violated bilateral non-proliferation commitments. Russia disputed the characterization. The weapons were sold. China has developed its own supercavitating torpedo capability, drawing on acquired Shkval technology. The specific performance parameters are classified. The general capability is confirmed. The guidance problem remains unsolved. Research is ongoing in Russia, China, and the United States. Guidance surfaces that operate at the cavity boundary. Acoustic systems designed for partial cavitation. Electromagnetic approaches. None have produced an operational guided supercavitating weapon at Shkval speeds. Before December 1977, 50 knots was not a design choice for a torpedo. It was the boundary of what physics permitted for a weapon moving through water. The Shkval pushed past that boundary. It has held past it for nearly 50 years, with all the operational limitations that required, and none of those limitations resolved. The VA-111 Shkval is still in service. The guidance problem is still unsolved. The nuclear warhead option is still available. And the speed record set in the Norwegian Sea in December 1977, 200 knots underwater, has not been matched by any other operational torpedo in the world. 49 years. An important note before we finish. On this channel, we analyze submarines, torpedoes, and weapons. We talk about horsepower, decibels, and chemical reactions. But the true history is known only by those who lived it. We strive for accuracy, but we don't claim to know the absolute truth. History is often a fog of war. And most importantly, any military action is a tragedy. Nothing is more valuable than human life. We study these machines not to glorify war, but to understand the cost of decisions and the price paid by the people inside the steel. If you want to understand that price, subscribe. See you in the deep.